Alright, so here we are, Physical Science 20. The lesson today is on empirical and molecular formulas. So we've talked about compounds, simple binary compounds. We've talked about compounds between ions that are polyatomic ions, sulfate and nitrate and those kind of things. And the formulas are usually determined by the charge on the ions, right, for ionic compounds. If we're talking about molecular compounds, the only way that we've been able to determine the formula is by given the name, right? If we give the name like nitrogen dioxide, we know what the formula is. It's NO2. So we are going to be talking about empirical and molecular formulas a little bit differently today. We're going to be able to write an empirical formula and a molecular formula given mass or percentage composition, which we've also just studied. So first of all, what is an empirical formula? An empirical formula, well, atoms combine in whole number ratios. So you should know this, that when we talk about atoms, you can't have a half or a third or a tenth of an atom combining with another third of an atom. They're whole atoms at least, right? The base minimum is whole number ratios. So when we're writing compounds, when we're stating compounds, we should have whole number ratios represented, even if we're talking about moles, right? It's whole number ratios. So therefore, empirical formulas have the simplest whole number ratios of atoms that are represented in the compound. That's the essence of the empirical formula. So it's the simplest whole number ratio. For example, if for some reason someone said, okay, well, we have sodium chloride and its formula is Na2Cl2, this wouldn't be the simplest ratio, right? Because we have 2 to 2, that's really can be reduced to 1 to 1. Thank you. So Na2Cl2 would not be written as Na2Cl2, it would be written as NaCl. Okay? Now, empirical formulas aren't always the way that they're written. They are sometimes actual formulas are not the simplest whole number ratio, and so sometimes the actual formula is called the molecular formula, which is not the simplest whole number ratio in some cases. So, for example, let me just erase this for you. For example, a molecular formula for hydrogen peroxide is H2O2. That's hydrogen peroxide. And notice this is not the simplest whole number ratio. So in most cases, we have empirical formulas are the proper chemical formulas for a compound. But in some cases, we have other formulas that are not the simplest. So that's sort of the distinction between empirical and molecular. Molecular formulas could be the same as the empirical formula, but sometimes they're not. So the question is, how do we determine an empirical formula or a molecular formula given either just percent composition or mass of the elements involved in a compound and so on? That's what we're going to learn today. So as you continue these notes and jot some of these things down, H2O2, hydrogen peroxide. So the empirical formula for hydrogen peroxide would be HO or H1O1, but that's not the actual molecular formula. And so we'll find out how to determine when the molecular formula is different from the empirical. Okay? So anybody have any questions so far, just in the first few minutes here, on the difference between an empirical chemical formula and a molecular chemical formula? All right. So what we're going to do is we're going to do an example where we take a look at finding an empirical formula from the data that's given. So anybody still writing this down? Okay. Okay, so I'll give you another second just to finish that up. You still writing? Okay, so here's the example. I want you to write this down in your notes. What is the empirical formula for a compound? And this is one type of question where we're given the mass. Okay, so we have a 2.5 gram sample of this compound. 0.9 grams of it is calcium. and 1.6 grams is chlorine. Now, if you're just given the two elements and you're told that they are forming a compound, between calcium and chlorine, you already have an idea of what that would be, right? Because you know that calcium is 2 plus, chlorine is 1 minus, so it's probably going to be calcium chloride like this. Okay? Now that's what you've been told. Because this is a simple question, we're going to explore how to do this type with a simple one. So you have that in mind already, okay? This is not how you do this question. That's not how you find the formula. But we already have this in mind that, hey, calcium and chlorine is probably going to form CaCl2. So we're just going to keep that in the back of our mind as we go through this. Let's see if this particular compound follows those rules. Okay, so step one, I just put out some steps on the side here for you. Step one would be, first of all, to determine the number of moles of each element in the compound. So what we need to remember is that in a compound, the ratio of atoms to each other in a compound is actually a molar ratio. It's not by mass, right? It's by moles. And we talked about that when we first talked about these formulas and when we talked about the mole just recently. So in a formula, the numbers, like if it was Ca1 and Cl2, those numbers would be a molar ratio. So we're going to find the number of moles of each. So let's go ahead and do that. So we have 0.9 grams of calcium. All right, so that is our mass, 0.900 grams of calcium. What is the grams per mole of calcium? Because we have to divide, remember, mass, to get to moles, you divide by grams per mole. So calcium should be 40.078. Does that look right? Okay. So when we do that, on our calculator, you get your calculator out. We're going to do 0.9 divided by 40.078. Oh, why is this not working? Okay, a little malfunction at the junction here. Okay, so you guys go ahead and do that on your calculator. Everybody got it? What's the answer there? As I restart my calculator. Oh wow. Okay, something's messed up with my calculator. All right, so what is this? 0.0224. Okay, so what does that give us? Does that give us grams? Does that give us moles? Does that give us, what does that give us? That's moles, right? That's moles of Ca. All right. And what about chlorine? Well, 1.60 grams of Cl. That's 35.4527. That's grams per mole of chlorine. Okay, that's the first step. So we find out how many moles are represented just by the masses that are given. Now what we do here for step number 2 is you can now see that there's a molar ratio here. I don't know if you can see this or not, but this right here appears to be half of this one. You see that? 0.022 and 0.045. That's about half. So step 2, to obtain the simplest ratio, the molar ratio between all those elements that are involved, you divide all the moles that you have, in this case we have 2 moles that are recorded, by the smallest mole value that you determined in step 1. And this should always produce a simple whole number ratio. If the masses are accurate, this should always produce a whole number ratio. It should be very, very, very close to whole numbers. So what this means is we're going to do, the smallest one is obviously this 0.02245. So what's the full decimal area? You might still have that in our calculator. 0.02245 what? What was it? You might still have it? 621? Okay. So that's going to be that's the smallest one. So obviously that divided by itself is going to be 1, right? So Ca, and however you write this, it doesn't really matter. But Ca is going to be 1, and Cl, okay, so now you go ahead and you go 0.04513, and there may be more decimal places there, but we divide it by the first one. And look at this. So you're going to get, when you round a decimal, you're going to get decimals that are a little bit off the whole number ratio, but we've got 2.00968, so that is 2, right? So you just round it to the nearest whole number. Now, if it's not really close to a whole number, then you might have a ratio that is like 2.5 or something like that. Okay? And if that happens, I'm not sure if that's going to happen. If you have like 1 to 2.5, then that's actually going to be 2 to 5, right? 1 to 2.5 should actually be 2 to 5. I don't know if you're going to run across that or not in these questions, but if you do, use these whole number ratios, and I'm going to put always here in quotes because I don't know if you're going to get questions that are going to be like that, but they always should be able to be a really easily determined whole number ratio. So in this case, it's 1.1 or 1.00 to 2.00. Therefore, we can confidently say that the formula is Ca, the 1, Cl with a 2. That is our empirical formula for calcium chloride. All right? So find moles first. Step 1, find moles, and then divide all the molar values that you have by the smallest one. Okay? Okay? So let's do another example here, then we'll let you get some practice in. So from percentage composition. So another type is, there's just one more really step for this, and that is in order to, if you're given percent composition, then the first thing you want to do actually is turn these percents into grams. And how you do that is it's pretty simple, right? If we have, let's see, so we have carbon is 40%, right? And we have hydrogen is 6.71%, and oxygen 53.3%. What is the empirical formula? All right. From percents, remember we're trying to get a relative ratio of masses. That's what we need to start off with. And if you think about percentage, it's really, percentage composition is just out of 100, right? That's what percent means, out of 100. So if you set the 100 there to grams, this would be the same as saying 40 grams out of 100 grams. See that? This would be 6.71 grams out of 100 grams. And this here would be 53.3 grams out of 100 grams. So because those are, that's how they're related to each other, you can simply say, let's go with 40, 6.71, and 53.3 grams. So those are the grams of each of those. You just basically use that number as a percent, use that as grams, and you can go from there. So it's really minor. But because we understand that they're all taken out of 100, they are relative to each other, this does work well for grams. Okay? So I'm going to give you a minute. Why don't you take a minute to finish this question using steps 1 and 2 from above now, right here. And go ahead and finish this question. Find out how many moles of each we have here. And then we'll divide by the smallest molar ratio to get the empirical formula. Okay, so take a moment to finish this question up here on your own. Okay, so this should be your molar ratio for the three elements that are involved here. I guess the only question that you might have is, which order to put them in. Do you do C, then H, then O? Do you do H first? Both carbon and hydrogen seem to be more on the positive side, but do you match carbon with oxygen or whatever? So this one actually, we would do it in this order, C, H, and O. So you'd have, because these are the molar ratios, and simplified here, 1 to 2 to 1. So you'd have C, H, 2, O. Okay, so that would be the empirical formula for this compound. Questions? At this point, if you did them in a different order, I would be fine with that. If you did this for some reason, if you did that too and you didn't know which one to put first, that's okay as well. All right. So yeah, just to officially kind of note that here, let's just write this down for notes here. Sometimes the ratio after dividing is not whole numbers, but the whole number ratio for the empirical formula should be easily attained from this new ratio. Okay, so if you put that down. So for example, if you have a 1 to 2.5, let's say. So let's say when you divide, you don't get a whole number, you get something that's very close to 2.5, 2.5001 or something like that. You can't round this to 3 and say 1 to 3. That's not okay. This is really close to 2.5. It should be 2.5. So then your empirical formula, because you can't have decimals, this would be 2 to 5. You just multiply everything by 2. So this would be your empirical ratio. Likewise, if you had something like 1 to 1.33, now that's too far away from 1 and too far away from 2. You can't round that. So 1.33 would be 1 1/3, right? Or that would be 1 to 4 over 3. So if you multiplied everything by 3, you would get 3 to 4 as a whole number ratio. Okay? So just note that. All right, molecular formulas. Let's talk about molecular formulas here now. Okay, so if you're asked to find the actual molecular formula, you find the empirical formula first. Okay? When you find the empirical formula, that is the simplest whole number ratio of all the elements in the compound. The molecular formula, as I mentioned earlier, may not be that exact empirical formula. It may be something else. But it's always going to be a multiple of the empirical formula. Okay? So what you want to do is you want to find the ratio between, and this is really important, the empirical formula mass and the actual molecular mass that will be given. And we'll do examples of this, of course. So whatever ratio that is, you multiply that ratio by the simplest molar ratio of the empirical formula. And that's how you get the actual molecular formula. And we'll do an example of that here right away. So just take a moment to jot those notes down.